thoughtful tone. 66 million years ago, a single rock erased the dominant species on this planet. Our current reality carries the exact same risk. Keeping all of humanity on one globe leaves us vulnerable to a single point of failure. This data visualization of the solar system highlights our limited options for relocation. Venus sits at 450 degrees Celsius under clouds of sulfuric acid, and gas giants like Jupiter lack a solid surface entirely. By strict process of elimination, Mars is the only viable candidate. To survive the deep future, human beings must become a multi-planetary species. The math is brutal. We either expand outward or we wait for a cosmic event to wipe out our only home. Getting there involves an agonizing logistical bottleneck. Because Earth and Mars travel at different speeds, a rocket takes 7 to 9 months to cross the gap, and we can only launch during a narrow alignment window that opens exactly once every 26 months. Grave, that tight window carries a heavy psychological weight. If you miss the launch, or if a critical system fails upon arrival, there is no immediate rescue. You are trapped there for months, and the world waiting for you is utterly lethal. The average temperature is minus 60 degrees Celsius. The atmosphere is less than 1% the thickness of Earth's, composed almost entirely of toxic carbon dioxide. Stepping outside without a pressure suit means a horrific death in roughly 2 minutes. Mars is our best hope for continuity, yet almost every physical characteristic of the planet is actively hostile to human biology. Historically, we haven't colonized space because of the economic absurdities. We spend hundreds of millions of dollars to build rockets, fly them exactly once, and let them drop into the ocean. The solution to that cost barrier is massive heavy lift capability, paired with total reusability. Engineers are currently testing ships capable of hauling up to 150 metric tons of payload to Mars at a single time. By landing these massive boosters and flying them again like commercial airplanes, the price per pound of cargo drops drastically. Spaceflight shifts from a custom multi-billion-dollar government experiment into a routine freight operation. Applying this commercial aviation model to space travel provides the massive volume of raw materials required to actually construct a permanent outpost off-world. Once we land those materials, the immediate threat is cosmic radiation. Earth has a thick magnetic field that deflects solar storms, but Mars lost its magnetic shield billions of years ago. We cannot ship heavy steel radiation shields 225 million kilometers across the solar system. Instead, scientists rely on in-situ resource utilization, a strategy of building with whatever raw materials are already lying around. Long before humans arrive, autonomous rovers will land on the surface, collect the iron oxide-rich Martian dirt, and run it through industrial 3D printers to extrude thick, basic structures. But the true long-term safety strategy requires digging. By moving habitats deep underground, astronauts will use meters of the Martian crust itself as a highly effective barrier against extreme temperature swings and deep space radiation. A self-sustaining city is too heavy to launch from Earth. Survival means manipulating the planet's lethal surface and turning it into our primary defense mechanism. The next hurdle is the dirt itself. The Martian surface is completely bone dry, and the soil is laced with toxic chemicals called perchlorates. Planting seeds in the ground will poison the crop. To get water, heavy machinery will drill straight through the rock to reach massive deposits of buried ice, heating it up and pumping it out as purified liquid. This flowchart illustrates why that extracted water is so vital. Using a process called electrolysis, we can split H2O molecules, piping the isolated oxygen directly into human habitats, while routing the remaining hydrogen to generate highly combustible rocket fuel. Expanding this same diagram, the extracted water also routes directly into hydroponic systems. By growing crops in nutrient-rich water under artificial LED sunlight, we entirely bypass the toxic soil. Mastering heavy water extraction and soilless agriculture effectively re-engineers a barren rock into an enclosed, self-sustaining biological loop. Looking decades ahead, the ultimate goal is terraforming. By intentionally releasing greenhouse gases and melting the poles, we could theoretically thicken the atmosphere enough to walk outside without pressure suits. Over multiple generations, the environment will reshape the people. Because Mars has only 38% of Earth's gravity, children born there will naturally develop taller, lighter bone structures and entirely different muscle densities. Geographically isolated and physically distinct, This population will eventually require its own framework of laws, its own governing bodies, and a unique culture tailored to deep space survival. Establishing this colony sets up a permanent biological divergence in the human species. Many argue that the billions spent on Mars should be spent fixing Earth, but history shows that extreme engineering required for space survival, like high-efficiency water purification and controlled agriculture, directly yields technological solutions for ecological problems back home. We are watching this exponential hardware development happen right now. The rockets are sitting on the launch pads, moving rapidly from science fiction into physical reality. Pushing outward into the hostile unknown transforms our single point of failure into a footprint that spans the solar system, providing humanity with its first true redemption.